Hello, my name is Isaiah Adu, and today I'd like to talk to you about my work on the optimization and analysis of terrain normal estimation. Off-road autonomous vehicles have to deal with a lot of complex terrain, and one of the particular things that be a challenge is slope terrain, because the approach of the vehicle and its orientation relative to the surface that it's driving on can play a significant role in things like reversibility estimation and rollover costing. Now, the first step in figuring out the vehicle's orientation relative to the terrain is by getting the surface normal. This normal can then be used to find the roll and pitch of the vehicle, which can then be used for cost functions. While this is very important, oftentimes it can be very computationally expensive. So this work focuses on developing a method of estimating those terrain normals in a more computationally efficient manner, allowing for real-time reversibility estimation. The current method that we use to estimate the terrain normal essentially works by looking at the position of each of the four wheel points on the vehicle and then using an elevation map in order to estimate a plane from those 4 points. Now, using that plane, we can get a normal vector, which we can then use to calculate the vehicle's roll and pitch. While this method is very accurate, it has the downsides of being very computationally expensive. So what we wanted to focus on was figuring out a method of decreasing the computation time while still maintaining similar accuracy. The proposed method would instead pre-compute all of those surface normals. What I mean by this is that essentially before it does any of the trajectory costing, the PI function, it would have an entire map of the terrain normals already generated in the first place. Those terrain normals can then be indexed by the costing function instead of having to compute the normal at each time step. Unlike the previous method, which uses the 4 wheel points to estimate a plane, this method instead uses the pre-computed normals at each of the 4 wheel points and takes the average of that in order to estimate the vehicle's normal relative to the terrain. Now, the way that this works is, first step is gathering the LiDAR information from the terrain. Essentially, the LiDAR collects a point cloud. That point cloud is then simplified to primarily look at the ground plane. Then it is turned into an elevation map, which can then be indexed in order to actually get the values we are looking for. So once you have that terrain estimation, you can then apply a Sobel filter. Once you get the X and Y gradient from the Sobel filter, you can convert them into a slope X and a slope Y vector. By taking the cross product of these two vectors, you can get the surface normal for the terrain at that point. By calculating this normal vector for the entire elevation map, you are able to get a normal vector field, which can then be used to compute the vehicle's roll and pitch angle at a given point along any specified trajectory. However, in order to actually get accurate results from this method, we wanted to figure out which kernel size had the most accurate results over a wide variety of terrains. To do this, we generated several sample terrains, all of which varied along the X and Y frequency, the amplitude, and with 3 different levels of terrain noise. By evaluating the error in the slope X and Y estimation, as well as the angle difference between the ground truth normal vector and the Sobel normal vector, we were able to determine that a 3x3 kernel provides the best result in all cases. In order to evaluate the effectiveness of this method, we used Rosbag data to calculate the difference between the compute time of the current method that we use versus the proposed method. After running this experiment, we found that the average compute time for the current method was around 139 milliseconds, whereas the proposed method, the average compute time was only 17.95 milliseconds, which is an overall reduction in 87.09%, which is very significant during live testing. For future work, we still have a lot to do in terms of field testing to verify that the speed improvements are on not just Rosbags, but actually in the field. And additionally, we want to add the normal area visualizations to RViz to allow for live debugging. I would like to thank Rachel and John for everything that they have done to make the RISC program just a truly outstanding experience, as well as to give my gratitude to the entire Air Lab team, and particularly Basti and Wencheng. They have been absolutely fantastic, and they've made this program a wonderful experience. I also like to give a special shout out to my two graduate mentors, Sam, Tristan, Mike, and I. They made my experience a great time, and they taught me so much as I was working on this. Thank you so much for listening to my presentation.